Light. It bathes our world in color, allowing us to perceive the beauty around us. But what exactly is this enigmatic phenomenon that shapes our reality? For centuries, scientists have grappled with this question, uncovering layers of complexity that continue to amaze. Early experiments suggested that light behaves like a wave. Like ripples spreading across a pond, light waves diffract around obstacles and interfere with each other, creating patterns of light and dark. However, as physicists delved deeper into the quantum realm, a startling discovery emerged. Light also behaves like a stream of particles, tiny packets of energy called photons. This duality, the ability to exist as both a wave and a particle, is one of the most intriguing mysteries of quantum mechanics. It challenges our everyday intuition and forces us to reconsider our fundamental understanding of the universe. In essence, light is a form of electromagnetic radiation, a self-propagating wave of electric and magnetic fields. These fields oscillate perpendicular to each other, traveling through the vacuum of space at the fastest speed possible, the speed of light. Light, as we perceive it, is but a tiny fraction of a vast spectrum of electromagnetic radiation. This spectrum encompasses a wide range of wavelengths, each associated with a different energy level. From the long wavelengths of radio waves to the incredibly short wavelengths of gamma rays, the electromagnetic spectrum is a symphony of light, most of which remains invisible to our eyes. At one end of the spectrum lie radio waves, the longest wavelengths of electromagnetic radiation. These waves, used for communication and broadcasting, have relatively low energy and can travel long distances through the atmosphere with ease. As we move along the spectrum, wavelengths decrease and energy levels increase. Next come microwaves, used in radar systems and microwave ovens. Infrared radiation associated with heat follows. We then encounter visible light, the only part of the electromagnetic spectrum that our eyes can detect. One of the most fundamental constants in physics, the speed of light in a vacuum, is approximately 299,792,458 meters per second, often rounded to 300,000 kilometers per second. This incredible speed is the ultimate speed limit in the universe, meaning nothing can travel faster than light. But what is it that travels at this mind-boggling speed? The answer lies in the particle nature of light. Photons. These massless particles, the quanta of light, carry energy and momentum, constantly moving at the speed of light. The speed of light is not just a number, it's a fundamental property of space-time itself. It dictates how fast information can travel and governs the interactions between all objects in the universe. Einstein's theory of special relativity, with its famous equation E+mc2, further cemented the significance of the speed of light, linking energy, mass, and the speed of light in an elegant relationship. Understanding the speed of light has profound implications for our understanding of the cosmos. It allows us to calculate the distances to faraway stars and galaxies, providing a glimpse into the vastness of the universe. Our eyes are sensitive to a remarkably narrow band of the electromagnetic spectrum, which we perceive as colors. This visible light, ranging from violet to red, represents only a tiny fraction of the full spectrum. But what about the rest of this invisible rainbow? Beyond the red end of the visible spectrum lies infrared radiation, invisible to our eyes but detectable as heat. This radiation is emitted by warm objects, allowing us to see in the dark using thermal imaging cameras. Further down the spectrum we encounter microwaves and radio waves, used in countless technologies from communication to astronomy. These waves, with their longer wavelengths, can penetrate through clouds and fog, making them ideal for communication and observation. On the other end of the visible spectrum, beyond violet, lies ultraviolet radiation. This high-energy radiation, emitted by the sun, can cause sunburn and skin damage. X-rays and gamma rays, with their even shorter wavelengths and higher energies, have the ability to penetrate through matter, making them invaluable tools in medicine and industry. Light interacts with matter in fascinating ways. When a beam of light encounters an object, it can be absorbed, reflected, or transmitted, depending on the object's properties and the wavelength of the light. This interplay of light and matter is responsible for the colors we see, the images captured by cameras, and the operation of countless optical devices. When light strikes an object, some of its energy is absorbed by the object's atoms, causing their electrons to jump to higher energy levels. This absorption of specific wavelengths determines the object's color. For example, a red apple absorbs all wavelengths of visible light except for red, which is reflected back to our eyes. Reflection occurs when light bounces off a surface. Smooth surfaces like mirrors reflect light in a predictable manner, while rough surfaces scatter light in various directions. This scattering is responsible for the diffuse appearance of most objects. Transmission, the passage of light through a material, is also wavelength dependent. Transparent materials like glass allow visible light to pass through with relatively little absorption or reflection. Opaque materials, on the other hand, absorb or reflect most of the incident light. Our understanding of light is deeply intertwined with our understanding of space and time. But what if there are more dimensions than the familiar 3 spatial dimensions and 1 time dimension that we experience? String theory, a theoretical framework in physics, proposes the existence of extra-spatial dimensions, curled up and hidden from our perception. In these higher dimensions, light might behave in ways we can only begin to imagine. Some theories suggest that light could leak into these extra dimensions, offering a possible explanation for the weakness of gravity compared to other fundamental forces. Others propose that particles could travel faster than light in higher dimensions, potentially allowing for shortcuts through spacetime. While these ideas remain speculative, they highlight the profound implications of light's relationship with spacetime. Exploring these theoretical realms pushes the boundaries of our knowledge and challenges us to envision a universe far stranger and more complex than we can currently perceive. Einstein's theory of general relativity revolutionized our understanding of gravity, describing it not as a force, but as a curvature of spacetime caused by the presence of mass and energy. Light, despite being massless, is still influenced by this curvature, its path bending as it travels through the gravitational fields of massive objects. This bending of light, known as gravitational lensing, has been observed astronomically, providing further evidence for general relativity. Massive objects such as galaxies and black holes can act as giant lenses, distorting and magnifying the light from objects behind them. The interplay between light and gravity is not just a theoretical curiosity. It has profound implications for our understanding of the universe. Gravitational lensing allows us to study distant objects that would otherwise be too faint to see, providing insights into the distribution of matter and the evolution of the cosmos. Furthermore, the extreme conditions near black holes, where gravity is so strong that even light cannot escape, continue to challenge our understanding of physics. Studying these environments through the lens of light's behavior opens a window into the most extreme realms of the universe. Despite its ubiquity in our lives, light is often misunderstood. Common misconceptions abound, leading to confusion about its true nature. Let's shed some light on these myths and clarify the reality of this fascinating phenomenon. One common misconception is that light travels instantaneously. While its speed is incredibly fast, it is finite. This means that light takes time to travel from one place to another, a fact that has profound implications for our understanding of the universe. Another misconception is that light is only visible. As we've seen, visible light is just a tiny sliver of the electromagnetic spectrum. Many other forms of light, invisible to our eyes, surround us, playing vital roles in various natural phenomena and technological applications. Some believe that light is not affected by gravity. However, Einstein's theory of general relativity tells us that gravity warps spacetime, and light, traveling through this curved spacetime, follows a curved path. This bending of light, observed astronomically, is a testament to the profound connection between light and gravity. By dispelling these and other misconceptions, we can gain a clearer and more accurate understanding of light and its role in the universe. Light is more than just a source of illumination. It's a fundamental carrier of information. From the images we see to the signals transmitted through fiber optic cables, light plays a crucial role in our communication and understanding of the world around us. Every photon of light carries energy and momentum, encoding information about its source and the environment it has traveled through. By analyzing the light from distant stars and galaxies, astronomers can determine their composition, temperature, and motion. The development of lasers, devices that emit highly focused beams of coherent light, has revolutionized numerous fields, from telecommunications to medicine. Lasers enable us to transmit vast amounts of information through fiber optic cables, enabling high-speed internet and data transfer. Furthermore, light-based technologies are at the forefront of scientific research. Microscopes that use light to visualize tiny objects, telescopes that capture light from the far reaches of the cosmos, and medical imaging techniques that rely on the interaction of light with biological tissues are just a few examples of how light empowers our quest to understand the universe and ourselves. While light's role in our physical reality is undeniable, some speculate about a deeper connection between light and consciousness. Could this fundamental element of the universe be linked to the very essence of our subjective experience? Some theories propose that consciousness arises from quantum processes within the brain, with photons playing a role in these intricate interactions. Others suggest that light might act as a bridge between the physical and mental realms, connecting our inner world of experience with the external world of matter and energy. While these ideas remain highly speculative, they highlight the profound mysteries that still surround both light and consciousness. The possibility, however remote, that these two seemingly disparate phenomena might be intertwined is a testament to the vastness of the unknown and the limitless potential of scientific inquiry. Exploring the potential connection between light and consciousness pushes the boundaries of our understanding, challenging us to consider the nature of reality and the place of our own awareness within the grand scheme of the cosmos. Despite centuries of scientific inquiry, light continues to hold many secrets. The future of light research promises to be as exciting and transformative as its past, with new discoveries and technological innovations poised to reshape our understanding of the universe and our place within it. One promising avenue of research lies in the realm of quantum optics, exploring the quantum properties of light for applications in communication, computing, and sensing. Quantum entanglement, a bizarre phenomenon where two photons become linked, sharing the same fate even when separated by vast distances, holds immense potential for secure communication and ultra-fast computing. Another exciting area is the development of new materials that interact with light in novel ways. Metamaterials, engineered materials with properties not found in nature, can manipulate light at the nanoscale, potentially leading to invisibility cloaks, super-resolution imaging, and highly efficient solar cells. The quest to understand light's role in the universe also continues. By studying the cosmic microwave background radiation, the faint afterglow of the Big Bang, cosmologists hope to unravel the mysteries of the early universe and the nature of dark matter and dark energy. As we delve deeper into the nature of light, we are bound to encounter even more profound mysteries and unimaginable possibilities. The journey to illuminate the unknown continues, driven by our insatiable curiosity and the promise of a brighter future illuminated by the power of light.